We are looking at FlashAttention-4, algorithm and kernel pipelining co-design for asymmetric hardware scaling.
Right. The core problem here is that the AI industry is moving to Blackwell GPUs, specifically the B200 and GB200 architectures. These feature asymmetric hardware scaling. Tensor core throughput has literally doubled, but shared memory bandwidth and exponential math units haven't kept pace.
FlashAttention-4 redesigns the pipeline to fix those exact bottlenecks. It overlaps matrix multiplication and Softmax. It emulates exponential math in software using FMA units. And it uses a new Two-CTA cooperative mode to cut shared memory traffic in half during the backward pass.
And the results are mic drop worthy. It hits up to 1613 TFLOPs per second, which is 71% hardware utilization. That is up to 1.3 times faster than cuDNN and 2.7 times faster than Triton on the B200s.
And as a massive bonus for developers, it is written entirely in Python using QTSL, which cuts compile times by 30x compared to C++ templates.
It is a total game changer for the ecosystem.
Okay, that was the rapid-fire summary. Welcome to AI Paper Podcasts. Whether you are an ML engineer trying to squeeze every ounce of performance out of a training run or an AI researcher, we are really glad you're here.
Absolutely.
Today, our mission is to do a real deep dive into exactly how the researchers achieved these massive gains. We're going to unpack how they essentially stopped treating the GPU as this uniform compute block and started treating it as a complex system of shifting bottlenecks.
Yeah, which is really the only way you can optimize at this level now.
Right. So let's start with this whole concept of asymmetric hardware scaling, because, when FlashAttention 3 came out, it was the gold standard, but it was heavily optimized for Hopper, for the H100s. Blackwell is just a completely different beast.
It is, and the numbers in the paper really show you why. The divergence is stark. If you look at the raw hardware specs from Hopper to Blackwell, the Tensor Core BF16 throughput doubled.
Wow.
Yeah, it went from 4,096 operations per clock cycle per SM up to 8,192. So the raw math muscle for matrix multiplication is scaling beautifully.
But the other parts aren't.
Exactly. The shared memory bandwidth stayed totally flat at 128 bytes per clock, and the MUFU, the multifunction unit that handles the exponentials for things like Softmax, that also stayed flat at 16 ops per clock.
Which creates this crazy situation on the roofline model, because you look at their roofline analysis and there's this huge aha moment where you realize matrix multiplication is actually not the bottleneck anymore.
Right. Not for attention workloads.
For a typical attention workload on Blackwell, the shared memory traffic and those exponential operations are exceeding the MMA. The matrix multiply accumulate compute time by like 25 to 60%.
Yeah, so basically if you just ran a naive implementation, your super fast tensor cores would just sit there twiddling their thumbs, waiting for memory fetches and softmax calculations to finish.
They're starved.
They're completely starved.
Yeah.
The surrounding silicon infrastructure just can't feed them fast enough.
So to fight this, the researchers really had to lean into some brand new Blackwell-specific architectural features. They're using much larger MMA tiles now, right? Like 128 by 128, which is double the Hopper area.
Double the area.
And they're using fully asynchronous tensor core operations. But the thing that really stood out to me was TMEM, Tensor Memory.
Oh, TMEM is huge.
Right.
It's essentially an architecture-defining feature for Blackwell. It's a 256 kilobyte warp synchronous on-chip memory that's dedicated to each streaming multiprocessor.
And why does that matter so much compared to the old way?
Because the tensor cores can write their outputs directly into TMEM, completely bypassing the register file.
Right, because register pressure was killing performance on Hopper?
Exactly. On Hopper, you had to store all your accumulators in the registers. That put a hard ceiling on how many concurrent operations you could keep in flight. TMEM totally relieves that pressure. That's actually what allows them to use those massive 128 by 128 tiles and pipeline much deeper without spilling data into slower memory.
So they've got this dedicated high-speed buffer. But that leads us straight into how they hacked the forward pass. Because even with TMEM solving the matrix multiply output problem, you still have that MUFU issue. The unit computing the exponentials for the Softmax is still physically stuck at 16 operations per clock.
Right. TMN doesn't fix the math unit disparity.
Yeah, so 8,192 matrix operations versus 16 exponential operations. That is a hard physical wall. How do you get around that?
By completely ignoring the hardware and doing software emulation.
Which sounds crazy.
It does. I mean, usually if you emulate a hardware math function in software, the latency penalty is brutal. But since the hardware MUFU is so hopelessly choked, The researchers took 10 to 25% of those exponential calculations and offloaded them to the standard FMA units, the floating point multiply add units.
Because the FMA units can run in parallel with the MUFU?
Exactly. They essentially parallelized a serialized hardware function across underutilized compute units. They used a polynomial approximation to emulate the exponential math. They break it down into an integer part, which they do with fast bit math, and a fractional part, which they approximate with a polynomial on the FMAs.
Okay, but put your ML engineer hat on for a second. If you're running a massive distributed training cluster and you hear that the foundational attention kernel is just guessing the exponential function with a polynomial, doesn't that sound like a recipe for exploding gradients? How accurate can a degree 3 polynomial actually be for a neural network?
I know, it sounds super risky. But the paper has all the data on this. If you measure it at the FP32 level, a degree 3 polynomial actually does have a pretty high error rate. It's like 600 times higher than the dedicated hardware instruction.
That sounds bad.
It sounds terrible. But you have to look at the whole pipeline. That FP32 output isn't the final destination. The Softmax output gets consumed by the next matrix multiplication, and it gets consumed as a BF16 value.
The quantization.
Right. When you round that FP32 value down to the much lower precision BF16 format, the quantization error completely swamps the polynomial error.
So it literally doesn't matter.
It doesn't. The data shows that after rounding, the degree 3 polynomial matches the hardware output to within one single BF16 ULP unit in the last place on 99% of all inputs.
That is just brilliant. The final data format is basically a low-pass filter for the approximation noise.
Yep. It's a perfect example of algorithm hardware co-design.
Okay, there's another massive optimization in the forward pass I want to touch on. The conditional softmax rescaling. Because standard flash attention constantly rescales, right?
Yeah.
Every time you find a new maximum value in a block, you have to renormalize all the previous results, which is a really expensive vector multiplication.
Right, and if they did that here, they'd hit another performance wall.
So how did they bypass it?
They realized they could tolerate some mathematical slack during the intermediate steps. In FA4, they just skip the rescaling update entirely unless the running maximum changes by a threshold of more than 8.0.
Wait, so the intermediate accumulators are just sitting there holding unscaled, technically incorrect values?
Yeah, temporarily. But they track the running statistics for the total scaling factors independently. As long as those stats are accurate, they can just apply the true denominator at the very end of the block.
That's incredibly smart. They bypass all those non-matmul operations that would normally stall the pipeline and just fix the math at the end.
Exactly.
Okay, let's shift to the backward pass because things get significantly heavier here. The forward pass is, what, 2 MMA operations per iteration?
Right.
But the backward pass is 5. You've got gradients for the output, the values, the attention probabilities, the softmax scaling, and the queries. The shared memory traffic is an absolute killer here.
It is. The roofline analysis for the backward pass is pretty brutal. With a standard tile configuration, shuttling operands back and forth from shared memory takes about 30% more clock cycles than the actual tensor core math. The whole system is completely memory bound.
So this is where the Two-CTA mode comes in.
Yes, this is a brand new Blackwell feature.
To explain this simply, it's like imagine the old 1-CTA approach is a single worker who has to go fetch a huge pile of bricks, which is our operand B, load them, and then build the wall. The 2-CTA mode is like 2 workers teaming up to build that same section of wall.
That's a great analogy.
Each worker, or each CTA, only has to fetch half the bricks from shared memory, but they work cooperatively to execute that single matrix multiply operation. So you essentially cut the shared memory bottleneck exactly in half.
You do, and it completely changes how they handle the DQ step, the gradient of the queries. Because these 2 CTAs are in the same physical cluster on the GPU, they can use DSMEM, which is distributed shared memory.
Right, so they can talk directly to each other.
Exactly. They exchange their halves of the DS tile, softmax gradient, directly over the cluster network. They don't have to route it through slower global memory. And a huge side benefit of this is that it cuts the number of global atomic reductions exactly in half.
And global atomic reductions are expensive, but they're also a nightmare for determinism, which is super critical for ML engineers.
Oh, absolutely.
Because if you're debugging a massive training run, global atomic reductions are non-deterministic. The thread scheduling is unpredictable. Memory access timing shifts. And suddenly your floating point rounding errors are accumulating in a different order, and your gradients look different every time you run the code.
Right, which is completely unacceptable for a production environment. So FlashAttention-4 has a deterministic execution mode.
But historically, forcing determinism means using semaphore locks, which just destroys performance, right? You serialize the memory writes and everything grinds to a halt.
Usually, yes. If you just lock the memory naively, the CTAs sit around idle waiting for the lock, and your TFLOPs just tank.
So how did FA4 keep the performance up around 1600 TFLOPs while using locks?
Smart scheduling. They treated it as a make-span minimization problem. To stop the CTAs from fighting over the lock, they use an LPT, longest processing time first schedule. They do this by swizzling the head in batch dimensions. Yeah, it basically scrambles the data access patterns and how logical blocks are assigned to the physical multiprocessors. By staggering the start times and the memory access, they drastically lower the chances that two CTAs will need the semaphore lock at the exact same millisecond.
Wow. And what about when you have causal masking, where half the attention matrix is masked out, so the compute load is super uneven across the blocks?
For causal masking, they flip it and use an SPT shortest processing time first schedule. The CTAs with the least amount of work get to go first, finish fast, and release their locks. That way, the heavily loaded compute blocks aren't stuck waiting in line.
That's just wild. The software is micromanaging the hardware's scheduling patterns to keep the performance high.
And it works. The deterministic mode keeps up to 75% of the performance of the non-deterministic version.
Okay, so we've talked about all these crazy low-level optimizations, but I want to pivot to something that is going to make the engineers listening very, very happy.
The Python part.
The Python part. Goodbye, C++ templates.
Seriously, good riddance.
Because traditionally, if you wanted to mess with flash attention kernels, you had to dive into CAG C++ template metaprogramming, usually using C2LS, and it is just a notoriously horrible developer experience.
It is so painful. The syntax is unreadable. The error messages are basically a novel of gibberish, and the compile times...
Compile times are the worst part.
Yeah, it just ruins your iteration speed. But FlashAttention-4 is built entirely in QTSL, which is embedded directly inside Python.
Which feels like magic, but you don't lose performance.
No, because it loaders the Python code directly to PTX parallel thread execution and then down to SAS, the assembly level. So you retain 100% of the low-level expressivity of C2S, but you're working in a modern, readable Python environment.
And let's just highlight the compile time numbers because they are staggering. Compiling the FA3 forward pass in C++ took 55 seconds. Compiling FA4 in Python takes 2.5 seconds.
Yeah.
And the backward pass went from 45 seconds down to 1.4 seconds. That's a 332x speedup.
It completely changes the way you work. When you're trying out a new kernel design or debugging a memory layout, waiting almost a minute to see if your code compiles totally breaks your flow state. Getting that down to under 2 seconds, it democratizes the whole field of attention mechanism research.
You don't need a PhD in GPU C+ architectures anymore.
Exactly. You want to build a custom flex attention variant or some crazy block source pattern, you can just plug these modular primitives together in Python.
Which really brings us to the big takeaway here. Why should you, the listener, care about all this if you never plan to write a custom cuDA kernel?
Right.
Because FlashAttention-4 isn't just a library update, it's really a blueprint for the future of ML engineering. As we've seen going from Hopper to Blackwell, hardware scaling is getting more and more asymmetric.
Yeah, the matrix math throughput is just aggressively outpacing memory bandwidth and specialized math units.
So we can't just wait for the next generation of chips to magically speed up our existing code. Squeezing performance out of these GPUs requires this exact kind of deep algorithm hardware co-design.
Hitting roughly 1,600 TFLOPS across sequence lengths, from 1K all the way to 32K. It proves that understanding your hardware roofline is the ultimate superpower right now. You have to know exactly where data movement is choking the pipeline, and you have to be willing to restructure your algorithms around physical silicon limits.
Right. Which leaves us with a pretty provocative thought to end on. We're seeing FA4 literally faking hardware features in software like the exponential math just to keep the tensor cores fed. If hardware continues this trend where the math units are 1,000 times faster than the memory and the specialized functions, will the future of AI infrastructure force us to emulate even more hardware in software?
It's a real possibility.
Are we entering an era where software just has to fake hardware features to get maximum utilization? It's something to think about the next time you look at a hardware spec sheet.
Absolutely.
Well, thank you so much for joining us for this deep dive into the shifting frontiers of GPU optimization. We appreciate you spending your time with us here on AI Paper Podcasts. Keep questioning those bottlenecks, and we will catch you next time.